All right, let's get it started. It says 12:30. We do have homework due tonight about Turing computable functions, so check it out. Let me know if you have questions about that. We only got a couple days left, I guess. I don't really have anything to say about that, but we will have a final exam. I'll say something, I guess, more about the test next time. Anybody have any vague questions at this point? No. All right, let's just get on with it then. So what we've been talking about are the languages associated to Turing machines, and I had an example. Maybe I'll just write it down to refresh our memory. We had this Turing machine from last time that does like this. Oops. BBL, and then an accepting state. Like that, right? This is a Turing machine, which we talked about this. What's weird about this is you have this little loop here, which moves to the right and then to the left again immediately. And what that means is in this Turing machine, if you actually on the tape have A followed by B, it will just go through this loop forever, because it'll read this A and move to the right, then it'll read this B and move back to the left, and read the A again, and so on. So this one actually, for certain types of inputs, this one can loop forever. This one, and we talked about this last time, we figured out the language of this machine is BX, where X is in AB star. This is all strings which are accepted on the machine. You can actually accept something if it begins with B, then that string will be accepted, all right? But if it begins with A, actually it's also possible to begin with A followed by A, and then it will just get stuck over here, and so that would be rejected. So that, for Turing machines, we call that the rejected language, and this would be AAX, right? If it begins with two A's, then you'll go across that first arrow and then just get stuck, and so that string will be rejected. AAX, X is in AB star. And also, just as a technicality, the empty string and also just A are also rejected. All right. And then there's the other language, which is the language of strings which make the machine loop forever. And that I'm going to write with an F. F is for forever. And this is ABX. Anything which starts with A followed by B causes an infinite loop in this Turing machine. All right. Infinite loops are not possible in a DFA or a stack machine, because, DFAs, you just read one letter at a time until you've read all the letters. So you can't have an infinite loop in that case. And a stack machine is similar. All right. Of course, we all know that real-life computers work like this too. There are certain things that you can do to a computer which make it enter an infinite loop. And this is basically always undesirable in a real-life computer. But, like when your computer freezes or something, that is typically caused by the software entering into an infinite loop, and so that it looks frozen to you when you're using it, but actually it's trying to do something over and over again and not actually getting anywhere, which is why it looks frozen. Computers in real life also experience this kind of infinite loop behavior. Everybody knows, hopefully your computer doesn't freeze all the time, but certainly it's easy to write, say, a Python program which will cause an infinite loop. So you could make it do that yourself, even if it's not going to do it on its own. All right. So here's a little bit of language. If f of m is empty, this means that if you have a Turing machine where the language of infinite loops is the empty set, what that means, if f of m is the empty set, then m never has infinite loops. This is good, in terms of a practical computer that you want to use. This is desirable to have a computer that can't make infinite loops. So then m never has infinite loops, and we call this a total Turing machine. A total Turing machine is one which never can make an infinite loop for any input. And actually, basically all the examples we've ever talked about are total Turing machines, like the Turing machine for a to the n, b to the n, which does this kind of marking thing. You can't make an infinite loop with those machines, all those examples that we've done. This one right here is not total. Not a total Turing machine. Total means infinite loops are impossible. But for that one, the infinite loops are possible. All right, M never has infinite loops, and in that case we call it a total Turing machine. And this is confusing language here, but I gotta go with it because this is what people really call this. Here's a definition. We say a language L is called recursive if it is the language of a total Turing machine. That is called recursive. Again, this terminology is borrowed from the lambda calculus, where that word makes more sense. It doesn't make a lot of sense in the language of Turing machines, but we still call it that. Recursive, if it is the language of a total Turing machine. If you recall last time, this is why I said this is confusing. Recursively enumerable is different. So recursively enumerable, which I'm gonna, from now on, I'm always gonna say RE. This means it's the language of any Turing machine, not necessarily total. All right, so you have to, this is a little bit of a pain to keep straight. Recursive means it's a total Turing machine, which means there are no infinite loops. Recursively enumerable means it can be done with a Turing machine, but that Turing machine may sometimes go into an infinite loop. All right. So maybe I'll just say that again. So L is recursive, means there exists a Turing machine with no loops, no infinite loops. RE means there exists a Turing machine. That's it. Maybe that Turing machine has infinite loops or not. So in terms of the big sort of nested circles diagram that I keep on drawing, the recursive is a smaller circle than the RE, because recursive has this extra qualification on it that there are no infinite loops for that machine. So the diagram, I'm going to draw the same old diagram that I've done many times before. This is regular languages, such as a to the n. There's the context-free languages, such as a to the n, b to the n, which is not regular, but it is context-free. And then we have the category of recursive languages. These are languages of a total Turing machine. So these are languages which you can generate by Turing machines which can never have infinite loops in them. And then we have the larger category of RE. And what remains sort of my major goal for the rest of the semester, we've only got this week basically, is to talk about what are some languages in each of these categories, and maybe, if we're lucky, what about out here, outside of the, so something out here means it's so crazy you can't even do it on any Turing machine, even if you allow the Turing machine to have infinite loops in it. All right? So my sort of large-scale goal for the rest of the week is to talk about languages in each of these three categories. But before we get to that, I want to say which of these categories corresponds to what we generally think of as useful computing machines. It would be this recursive category here. I'm going to try to put a big, that's kind of ugly. I meant to put sort of a big fat. This region here is what I would describe as, these are like useful machines. So anything outside the category of recursive, you should think of as those are things which you can't really do on useful real-life machines. And why I say those ones are useful but not these, even though these RE languages, you can compute them using Turing machines. So from that point of view, this sounds like a real-life machine that you could, in theory, create. But actually, it's this category which are the kind of real-life useful ones. And the reason is because, so I will say languages in RE, but not recursive, are ones where you may encounter, I will say, long computing times. You know, if you ask me, the usage of a Turing machine typically is, I show you a string and the machine tells you if it's accepted or not, all right? Now, sometimes those machines will have to take a long time for computing, but in the recursive category, in this smaller one, a long computing time, if you plug in a string and ask it to tell if it's rejected or accepted, a long computing time is a nuisance because you have to wait until it's finished. But, you know, it's no more than a nuisance. But in this category, a long computing time is indistinguishable from an infinite loop. And so if the machine is taking a long time, you have no way of knowing if it's ever going to finish and the string will be accepted or rejected, or if it's an infinite loop and you should just stop waiting. So languages in the RE category are ones where you may encounter long computing times which are indistinguishable from infinite loops. Indistinguishable. This is like getting ghosted by that fine female at the club. Is she just not writing me back because she's really busy the past couple months? Or is she really never going to write me back? If you know for sure there are no infinite loops, then you can just wait until it's done, if you have some kind of guarantee that it's going to be done. But if this is a machine which is capable of infinite loops, sometimes you have no way of knowing whether it's actually going to stop or not. And that means, from a practical point of view, you cannot use this machine to tell you if a string is accepted or rejected, because you might have to wait a long time and then you won't be able to know if it's accepted or rejected. All right? So that's why I say this smaller category is actually the useful machine. So when people talk about Turing machines being useful for real-life computation, really the useful ones are in that smaller category, the recursive, not the RE category. All right? Okay, that's what I wanted to say about that. Now, perhaps we are getting a bit ahead of ourselves when I'm talking about using Turing machines in the real world, because, of course, nobody uses actual Turing machines in real life. A Turing machine with a tape and a head on it, when you think of computing machines, they don't really look like that. I would like to talk briefly, we'll come back to this little diagram and try to fill in some of these question marks, although maybe not today, I'm not sure. But I would like to talk about a little bit briefly about Turing machine variations. Can we think at least a little bit about what would happen if you gave the Turing machine a little bit more capabilities or changed the structure or the setup of the Turing machine a little bit? How would that change anything? So, for example, I would like to think about our Turing machine always moves left or right. All right? Every step, the head is required to move to the left or to the right. Now, you might ask yourself, ask your friends, what if we had a Turing machine that was also allowed to stay still? Actually, somebody asked me about this, I don't know, a couple times ago. What if we also allow the Turing machine to stay still? let's say I would write that like something like AA bar S, where S means you don't move, you just stay there. And then, of course, go to the next step in the diagram or whatever, but you don't move, you just stay still, all right? Does that result in a different category of machine? Like, is that machine, which is allowed to stay still, is that machine actually capable of calculating or generating different languages from the other machine, which is not allowed to stay still? Or is it just like a sort of a surface level change? All right, that's the question that I would like to answer. Let's call this is a made up name, a Turing machine that stays. Unlike that girl at the club, am I right? This is a Turing machine that in each step it doesn't have to move left or right. It can also just stay still on the tape, all right? My claim is that actually this doesn't really make a difference. If your Turing machine is also allowed to stay put, it still can do more or less the same stuff that an ordinary Turing machine can do. And the way that, this is actually not so hard to prove. I'm going to write this like a theorem, just to demonstrate the proper way to be thinking about this is, so I'm going to say it this way. Any Turing machine that stays can be simulated by I'll just say an ordinary Turing machine. And by simulated, what I mean is you can make another ordinary Turing machine that doesn't stay, but it has all the same languages, the same accepted language, the same rejected language, and the same looping language. So by this simulated, I mean there exists a Turing machine with the same L of M, R of M, and F of M. Meaning, whatever you can do with the Turing machine that also stays, you can do the same thing with an ordinary Turing machine, which always moves left to right. This is what I'm saying here. All right? And that's what I mean by simulated. One machine can simulate another, even if they have different capabilities. Whatever the one can do, you can do on the other one. And whatever the other one can do, you can do on the first one. All right? So here's how we would demonstrate that. Any Turing machine that stays can be simulated by an ordinary Turing machine. This is not a big idea, so I'm going to just to set it up here, I'm going to say let M be a Turing machine that stays. And I'm going to try to be very specific about how we could sort of create another ordinary Turing machine that doesn't stay, that has the same capabilities. So I'm going to say something like that. If in M we see an arrow that looks like this, let's say state A goes, I don't know, I'll say X, Y, S to state B. So if you see an arrow that stays in the original machine, we can convert it to, this is not so hard. If you invent another state, you can convert that into a set of two arrows on a machine that does not stay. Anybody feel like you know what I'm thinking about here? How can I change this in a way, maybe it'll take two steps instead of one step, but you can make it do the same thing without ever staying put. Yeah.
X, Y, right, and then Y, left.
Yeah, he says X, Y, R. So you make the change on the tape and then move to the right, and then you just move back to the left. And after doing that, it is as if you made the change but didn't move. Now the other arrow here, you really need to, I think what he said was YYL to move back to the left, which sounds good to me, although what's on the tape in this position is not Y, right? Because this says, it's like you have two spots on the tape. This says you change one of them, which used to be X, is now Y, but then you move to the other one. You actually don't know what's on the other one, so you have to, right here, you have to put labels for every possible thing that could appear in the other one. So you could put something like AAL and also BBL and also whatever. I'm just going to write something like star, star, L, meaning whatever you see in that spot, I don't care what it is, you just leave it like it is and move back to the left by one spot. All right? If you like, you could write out all the letters that might appear in the alphabet and put something like AAL every time. All right? But anyway, I hope everybody agrees these two things are equivalent, right? This has changed the x to a y and stay put. This has changed the x to the y and moved to the right, but then immediately moved back to the left without doing anything else. So they're the same, right? And so I will just say, in this way, we convert M into an ordinary Turing machine. Every single arrow that you see with a stay, you just do this to all of them, right? We convert M into an ordinary Turing machine that is entirely equivalent. The end, all right? This is the end of the proof. You do that for every arrow that has an S on it, you convert to one of these things which just goes back and forth. And you end up with a Turing machine with the same capabilities. Now, the machine you end up with maybe is like slower. It has to do 2 steps where the original one only had to do 1 step. But in terms of the theoretical capabilities, not taking like efficiency into account, but just the theoretical capabilities, it has the exact same capabilities. All right. So when I said we were, what I said here, I want to talk about Turing machine variations. In a sense, like this is not even a variation. Like technically speaking, it is, but it doesn't actually make a different kind of machine. It makes another machine which is equivalent to the original Turing machine. All right. Would you believe me? I'm not going to go through the same detail arguments, but I will just say this is similar for a Turing machine that, say, jumps. I don't know if you ever wondered about could there be a Turing machine where it's not only allowed to move left or right, but it could move, like, jump to the right by 3 steps or something like that? Make it so that any of those arrows, rather than just saying R or L, they could say, like, R cubed or something like that, which would mean move to the right 3 times. That I might call a jumping Turing machine. For exactly the same reasons, all of those are just equivalent to the ordinary Turing machine. All right? They may be a little bit more efficient, but they're not actually theoretically different. So a Turing machine that jumps, these are all equivalent to the usual Turing machine, the ordinary one. All right? And by equivalent, I mean you can simulate them using an ordinary Turing machine. So they don't actually give you a theoretically more complicated machine. All right? These are variations in terms of how the head moves. You could also think about variations in terms of the structure of the tape. So how about this one? What about if we have, instead of we imagine the tape as being a long, infinitely long thing which stretches out in both directions. What if, I don't know if you ever thought about this, what if we have a 2-dimensional 2D tape? Huh? How about that? So the tape, instead of being a sort of a long, skinny strip of paper, what if it's like an actual 2-dimensional grid of locations, and the Turing machine can move left, right, but it can also move up and down? Is that any different from an ordinary Turing machine with an ordinary 1-dimensional tape? The answer, again, is no. So what if we have a 2-dimensional tape? I will say this can be simulated by a normal, sort of, I will say, 1-dimensional Turing machine, which uses pairs on the tape, right? Everybody knows points in a 2-dimensional grid can be described using pairs. And so if you can imagine a Turing machine which has a 2-dimensional tape, you can do that same stuff on a 1-dimensional tape. You just, instead of writing on the tape just one thing, you write a pair of things. And then this will simulate a tape which has 2 dimensions, right? What about a 3-dimensional tape? No, it's the same thing. You use, instead of pairs, you use triples. There's no difference really. 4-dimensional tape, it doesn't matter. All right, increasing the tape. This is like jacking up the dimension of the tape. You could also think about, how about just like 2 tapes, 2 separate tapes? Again, this can be simulated using a tape with pairs written on it. All right, you just have to keep track of both tapes at once. But if you're using pairs on your one single tape, there's no problem. So I will say again, use pairs. Yeah, I mean you'd have to work out the details slightly differently, but none of these are actually different types of machines. Can anybody think of another way to change the capabilities of a Turing machine? I've suggested changing the way the head can move. You could think about changing the structure of the tape. Nothing comes to my mind in terms of changing the machine in some other way. What if it was allowed to write letters in 2 different colors? Huh? I would say that's basically, if when it writes, it can write in black or in red. I would say this is basically the same as having 2 separate tapes, one with all the blacks and one with all the reds. But then the 2 tapes you could just do using pairs. It doesn't matter, all right? I'm gonna say, maybe, I don't really have a proof of this, but it is more or less a fact. I will say anything you can think of to add features to the Turing machine results in equivalent machines. Anything you can think of to add features to a Turing machine really just ends up resulting in equivalent machines. I said I'm not going to try to prove this because actually this little phrase right here is doing a lot of work here. Anything you can think of. How do you prove that? Well, it's easy if I'm talking to an idiot or something. Like this has to do with what you're capable of thinking of. Now, it turns out actually, and this is something that by the end of the week we will have discussed this entirely. Actually, there are non-equivalent, I will say, improvements you can make. But you would never think of them. They're crazy. They're like very, very weird and not the kind of thing that an ordinary person would ever think of. But we'll talk about them eventually. But I will just put that sort of in brackets for now. There actually are some sort of non-equivalent improvements that you can make to the Turing machine, which give it, if you give it some kind of like magical powers or something, you should be imagining something like maybe you've heard of a quantum computer, which can do things which kind of violate the classical laws of physics. This is possible, and it makes the capabilities of such a machine different from the capabilities of an ordinary computer. But you have to do something really crazy in order to make a Turing machine any better than the normal Turing machine as described originally by Turing. Yeah.
Could you make a Turing machine random?
Yeah, this is a good thing to wonder about. What if I give it some kind of randomness capabilities? I would say that is definitely different from the classical Turing machine, but it also kind of falls sort of outside the realm of, like I'm trying to think of things in terms of, basically in terms of this diagram. You know, the ones inside this blue circle is the domain of the Turing machines, and also this RE. And really the questions that I'm asking could also be phrased in terms of, can you make some other kind of machine that goes even beyond this circle? Anything you can think of to change the machine, it's still going to stay within this domain. Now, what if we add randomness? I would say this entire discussion is not really equipped to handle randomness because, for instance, all these languages are about, is the string accepted or not? Now, if you allow the machine to have some kind of randomness, it means like, if I ask it if AABB is accepted, maybe it says yes, it's accepted. But then I immediately ask it again, and maybe it says no this time because there's some randomness involved. That is definitely different from a classical Turing machine, but it also makes it so that The thing that I'm talking about is not really even of the same type anymore, because it doesn't just give me the same answer when I ask about accepted, rejected strings. This is a great point. Something you probably know, that real-life computers are not really capable of randomness. They do this kind of pseudo-random number generation. Okay. What I want to say is there's actually one very notable variation of the Turing machine. So I will say this is an important Turing machine variation. And this is referred to as the von Neumann architecture. The von Neumann architecture. This I'm not going to describe in complete detail, but you know, the Turing machine consists of a head with a tape, and the head can move around on the tape and change the values on the tape. The von Neumann architecture is a different kind of imagination about the general shape of the machine. And what the von Neumann architecture has is it has an input device, it has an output device. On the Turing machine, these are kind of both the same thing. You use the tape for the input and also for the output, which is a little confusing if you were trying to use that in the real world. It also has a memory unit, and it has a central processing unit, also known as the CPU. All right? And these things in the von Neumann architecture, they are sort of schematically organized in this way. You have the input device, which somehow pushes strings or other kinds of data into the CPU. The CPU, as it's doing its thing, is allowed to read and write from the memory unit, which acts kind of like the tape of a Turing machine. And then that CPU, it does a bunch of stuff using the memory unit, and then eventually it sort of spits out an answer to the output. Right? This is called the von Neumann architecture. It is basically like a Turing machine with sort of with like segregated tapes, right? You could imagine the input is like a tape, and then the memory is another tape which you can read and write from, and then the output is another tape which only gets written. You don't read back from the output, all right? But anyway, this you may recognize as the basic structure of a real-life computer, right? Real-life computers work in this way. Now, a typical computer like this iPad that I'm using, it has a CPU, which is the chip inside of it. It has memory inside of it. The iPad doesn't have a specific input device. It has many input devices, but basically the input for this iPad mostly comes through touching the screen, right? It also has input because it has like a Wi-Fi receiver in it that can act as input, and it has a Bluetooth and other kinds of things. It has many input devices, and it also has many output devices. The screen is the main output. It shows me things on the screen, but then it can also output things over the network or whatever. But anyway, this is the shape of basically every computer that you've ever used. So I will just say something like, all modern computers are more or less like this. And because this is essentially a souped-up Turing machine, like it's like a Turing machine with several different tapes that have different purposes. All modern computers are like this, and so they are all equivalent to the Turing machine, right? What I mean by that is, in theory, any calculation that you can do with a von Neumann style computer, like a real computer, you can do that same calculation on an abstract Turing machine with a single tape. Does that mean like you could play Fortnite on an abstract Turing machine? The answer is technically yes, although the abstract Turing machine doesn't have the same kind of input and output that is generally required to play Fortnite. But if you could somehow play Fortnite using strings, as the input and strings as the output, then in theory, you could translate the full source code to Fortnite can be translated into a giant Turing machine diagram. It would not be very, I don't recommend it. It would be much, much less efficient because converting actual code into Turing machine diagrams results in extremely complicated diagrams. But in theory, it's possible, all right? Great. So in this way, this is like one reason, Turing, when he sort of had this big idea back in the day, he didn't refer to these things as a Turing machine because it's lowbrow to name something after yourselves. But the Turing machine this is why it is described as a universal machine. And this is what Turing actually called it in his paper. He called it the universal machine because he had this idea that this very simple looking thing was actually capable of any computation you can imagine. It's called the universal machine. Nowadays, if somebody asks me what is meant by the phrase universal machine, I would say any machine which is equivalent to like a real life computer, like a von Neumann type computer. Any such computer can be simulated by a Turing machine, and so they are called the universal machines, all right? Any thoughts about that? You might wonder, actually, can a Turing machine simulate a quantum computer then? Because a quantum computer is sort of fundamentally different from this kind of a thing. Although it turns out, actually, quantum computers, they operate according to different principles, but the difference between a quantum and a normal computer is really a matter of algorithmic speed. It's not about can it do different things. So it turns out, actually, and this is not easy to see at all, but it turns out that quantum computers, from an abstract point of view, they also have the same capabilities as, say, a von Neumann computer. It's just they can do it a lot faster, which is why people want to make them. But they're not theoretically different in terms of the algorithms they can calculate. All right. Anyway, what I want to talk about is let's get to some of this business about these languages over here. The first thing, so I would like to discuss. It now occurs to me. This was a long time ago, but there doesn't have to be a question mark here. We already know examples of languages which are outside of the context-free category. Anybody remember? There was actually one specifically that we talked about. It is more or less ordinary looking language. You can write it kind of like these ones, but it's not context free. Remember? Yeah, A to then, B to then, C to then. You can do that using a Turing machine. We've actually done that example. So sorry, can I just flip back? A to then, B to then, C to then is an example of this. All right? That is recursive but not context free. Recursive meaning you can make a Turing machine that accepts that language, and it is a total Turing machine. That is, it never enters any infinite loops. If you go back and look at the example we did for A to then, B to then, C to then, it's not so hard to convince yourself looking at that example that there can never be any infinite loops. Question?
Is A to then, B to then, C to then, D to then?
Yeah, that's the natural thing to say here. This one must be A to then, B to then, C to then, D to then, right? That must go right here. Anybody have a feeling about that? I kind of feel like whatever we did in class for this example, couldn't you just like do the same thing and put a D on the end? The answer is yes, you can. So actually putting the D on the end really doesn't get you out to this category. And what if, can you imagine, what if we put an E on the end? Does that get you all the way out here? Something which could never be computed by any Turing machine at all? No, of course not. Like when you're out here you're talking about things which could never be calculated by a Turing machine, which means could never be calculated by a real-life computer. Certainly a real-life computer can tell the difference between A to then, B to then, C to then, D to then, E to the N, right? Versus D to then, it doesn't matter. That stuff is irrelevant when it comes to doing this on a real computer. So yeah, these are the only things that we really need to discuss. And I would like to talk about this one right now. So a recursively enumerable language, but it's not recursive. And this is actually something that we talked about on the very first day of class. And I would like to refresh your memory about this. So let's talk about a non-recursive language. What this would be is it's a language which can be the language accepted by a Turing machine, but that Turing machine may have infinite loops in it. And this is the language associated to something called the halting problem. And we did discuss this on the very first day of class. A non-recursive language. It is the language associated to the halting problem. So I'm going to, I'll refresh our memory in case you don't remember all the way back on the first day of class. I tried to explain this with fairly simple language back on day one, but we're a little more sophisticated at this point. So the question, the halting problem as a problem involves, given a Turing machine, let's say M and some string X, asks the question, does M accept X? That's the question. This is called the halting problem. Is there a way to tell if the Turing machine accepts X or not? Actually, it's not accept, sorry. I mean, does M halt on X? And what I mean by halt on X, I mean M does not do an infinite loop. So I don't really care about accept versus reject, but it's just does it have an infinite loop or not? All right, that's the question. If somebody gives me a Turing machine and a string, can I decide whether that Turing machine halts on that string or not? This is called the halting problem. Halt means it either accepts or rejects, but it does not loop forever. All right. So I'm going to try and translate this into a specific language. I'm going to call this LH. This is the language of the halting problem. And I'm going to write, this is going to look a little weird, but it is a set of all strings that look like this. I'll say M hashtag X. And what this means is M is a string encoding of a Turing machine, and X is some string for which M halts on X. This is very weird. I might as well say everything we talk about from now until the end of the course will be very weird, because we're trying to get outside of that category of recursive languages. It has to get weird. So what this is, it is the language, I will refer to this as the language of the halting problem. Language of the halting problem. It is a language consisting of, this says, a string encoding of a Turing machine. What I mean by that is you take a full Turing machine and somehow change it into a string. You could, any Turing machine can be encoded as a string of zeros and ones if you like. I don't want to get into the details of how this is done, but I think everybody knows that actually any piece of information, if it's stored in a computer, is somehow converted down into a string of zeros and ones, right? So I imagine you take a full Turing machine diagram, turn it into a string. It could be zeros and ones or whatever else you want to use. That's what M is. So M is a string which describes a Turing machine. And then X is a particular string which you intend to feed into the machine M, all right? And it goes in this set. This set consists of all of the strings that look like the machine, this hashtag followed by a string, so that M halts on X. The purpose of the hashtag is just to separate these two strings so that you can tell which part is which part. All right? This I'm going to refer to as the language of the halting problem. It consists of strings that look like some machine followed by some string, where the machine halts when you stick the string into it. All right? Now, this actually is, this LH is recursively enumerable. It is RE. On our diagram, that's the widest circle. It is inside of the widest circle. It's not all the way out. It is RE. That's because if we want to test if M halts on X, I'm trying to tell you how you can make a machine that actually generates strings like this. If you want to test if M halts on X, you just simulate M running on X and see if it halts or not. All right? So it is possible to make this calculation using a Turing machine. The problem is, this last thing that I said here is this thing about RE versus recursive. See if it halts or not may require sort of waiting for an infinite length of time. So in real world purposes, this is not a legitimate algorithm. But in the context of RE languages, that is the language of a Turing machine, even though that Turing machine might have to run forever to make its computation, this is perfectly allowable, all right? So that's why this is RE. So remember, this means we can do it with the Turing machine, but it may run forever, right? And what I just described here is a way to make the calculation if you allow sometimes, if you're allowed to wait forever to see the answer, all right? This is outside the bounds of like what a real world computer is supposed to be able to do. But it is still technically inside the RE category, all right? Because I can do it in the language of Turing machines. It's just, they may have to run forever, all right? So that means on my diagram up there, this language, I don't want to keep on scrolling. It's inside this region. I want to show that it's outside of the recursive, right? So let's show that LH is not recursive. That would put it in the appropriate spot. What I'm trying to show is that this is an example of a language which is recursive. I'm trying to show this language is here, right? In between, outside of the recursive category, but inside of the RE category. So,
Oops, sorry, wrong room.
all right, I think we can do this just in our remaining, plenty of time. All right. So this I am going to write down using a little argument by contradiction. So maybe I'll write this like a theorem. LH is not recursive. This is very weird, but this argument is actually something that I said on the first day of class. I said more or less the same thing that I'm about to say right now. LH is not recursive. So the proof is going to be proof by contradiction. So for a contradiction, let's assume LH is recursive. What that means? That means, so there exists a total Turing machine which computes LH, right? That's what it means to be recursive. Total Turing machine, that means it can do this without having any infinite loops. That's what total Turing machine means. I would say, i.e., there exists an algorithm. Would you mind if I use that word? Algorithm meaning there's just some method that you can describe to tell whether any m halts on some x, right? Because LH, what it is as a language, it consists of all the strings m together with x so that m halts on x. So if you're saying there is a total Turing machine, it means there is an algorithm, which actually you don't have to wait an infinite amount of time. You can actually get the answer that will always tell you if any Turing machine halts on any input that you give it, all right? And now we're going to do something somewhat ridiculous with this algorithm. So let's build a new algorithm, or I will say a new machine to do the opposite. What I mean by that is with the input, if the input, we have to imagine that the input somehow looks like this. What if you imagine this is kind of like running this Turing machine on itself? Which is weird, but it should be allowed to, because you can plug any string into the machine you want. You can plug in the encoding of the machine itself and run it on the machine itself. So I'm going to say, I'm going to build a new machine. Maybe my new machine will be called N to do the opposite. So I'm going to describe what N does. When the input is M followed by M, N will halt if M doesn't halt on M, and N doesn't halt if M halts. All right? So this other machine, N, is meant to do the opposite of whatever M does when you run M on itself. So if M on itself stops, you make N so that it never stops. And if M on itself never stops, you make N so that it does stop. All right? Ordinarily, this would be impossible to do because you never know if it's going to halt or not, because you might have to wait forever before you can tell. But I'm imagining that this actually is possible. All right? We're trying to get a contradiction. The final contradiction, I can see some people are beginning to lose it with this stuff. This is pretty far out, I know. The final contradiction is obtained by asking the question, what happens if we run N on itself again? If we run N on this N hashtag N, all right? So really what I'm doing is just what I wrote up here, I'm just plugging in N instead of M. And let's see what these lines will say. So then, the first line says N halts if N doesn't halt on N. I'm just plugging in N. And the second line says N doesn't halt if N halts on N. How do you like that? If you are still capable of following along here, you will realize both of these lines are nonsensical, right? This says N halts if N doesn't halt, and this says N doesn't halt if N halts, all right? Neither of those can be true. And so this is the contradiction. All of this business leads to this logically nonsensical situation here. So I will just say this is impossible. There can be no such machine that behaves in this way because this is immediately self-contradictory. This is like the the guy who says my twin brother always lies or something like this kind of a thing. I don't know you know what I'm talking about. It's like saying I always lie, something like that. This is impossible. So all of this means that no such machine N or M can exist, right? And all of that means, that I was looking for a contradiction all along. So that means that L, the language of the halting problem, is not accepted by any total Turing machine, all right? And here ends the proof. So I will write my little diagrams again. I have regular, context-free. Outside of context-free is recursive. You have more or less ordinary-looking languages inside of there. If you want to go outside of there, though, there are other languages. One is this language of the halting problem, and this is RE, but not recursive, right? This language of the halting problem. All right. This will immediately tell us, I said before, any way you can think of to improve the capabilities of a Turing machine results in the same machine again. But what we've actually shown is the fact that this is out here. What this means is that this is sort of the short version. You can tell your friends at dinner. This means no total Turing machine can solve the halting problem. Just to be more specific, what that means, i.e. it means no Turing machine, no total Turing machine can take something that looks like M hashtag X and tell whether or not M halts on X. All right. Actually, this is an interesting fact that your friends at lunch may actually be able to understand. You don't have to say all of this stuff, but you can say, this is a problem which no Turing machine is capable of solving, and that means no real-life computer is capable of solving this problem either, right? Real-life computers, like the phone in your pocket, cannot do this kind of computation. They can't tell. If I describe to you another Turing machine or another real-life computer and ask you if that machine is going to have an infinite loop or not with a certain input, that is just straight up an impossible question for a real-life computer to answer. The best the computer can do is to take that code or whatever it is and try to run it on X. Maybe it will stop, maybe it won't. But if it doesn't stop, that's not a guarantee that it's an infinite loop. It just means you've got to keep on waiting. It's the same sort of ghosted at the club scenario, right? This is the halting problem. Now, maybe now that we know a little bit more, last time I said this, can anybody now think of an extra capability that you could give to a Turing machine that would actually make it more powerful? I just described to you a problem that no Turing machine can do. That means if your Turing machine, by some magic, could do that, it would actually be more powerful than an ordinary Turing machine. All right? And there's a name for this. So this is called, so I will say, an actual improvement to the Turing machine. An actual improvement. This is called a Turing machine. I didn't make this up. This is called a Turing machine with halting oracle. You imagine the Turing machine has some kind of magical power where at any moment, instead of moving to the right or moving to the left, it can somehow magically solve the halting problem. That makes it more capable than the ordinary Turing machine. So a Turing machine with halting oracle, this is an ordinary Turing machine which it has the ordinary diagram or whatever. I will say, in addition to moving according to the diagram and the tape or whatever, can also solve a halting problem. All right. This is called a Turing machine with halting oracle. Such a machine would actually be more powerful. So this is actually, maybe I'll say in more technical language, these cannot be simulated by any Turing machine. Right? These would be actually more powerful. Now, can you make such a thing in real life? No, or at least not according to the laws of physics as we know them. All right, this is there is no known way to make some kind of actual real life halting oracle. But if you want to improve a Turing machine, this is how you would have to do it. All right. Do you agree with me now that this is not something that an ordinary person would think about? This is what I said. There are ways to improve the Turing machine, but not anything that you would ever think of. This is the kind of absurd kinds of things that you have to do. There's an interesting thing you might wonder, okay, Turing machine with halting oracle. Is that somehow the ultimate machine? Like, can that now compute anything that you can imagine? The answer is no. Actually, a Turing machine with halting oracle, there are yet more sort of ridiculous abstract questions that you can prove are not answerable, even with the halting oracle. And you could say, okay, man, those other things, give me an oracle for those other things too. Then you get a machine which can answer any of those questions. Again, it turns out, this is like an interesting sort of stoner type question to think about. If you just keep on giving more and more oracles to your machine, can you eventually make a machine that can do anything? And the answer is actually no. You can prove no matter how many oracles the machine has, there are always some questions, some ridiculously abstract questions that cannot be answered by any of those oracles. So if you have sort of finitely many oracles, is not good enough to answer any question. And even if you have infinitely many oracles, you can construct questions which are not answerable. All right. So I don't know if that sounded interesting. It should sound fairly crazy to you. So when your friends ask you, this is something that was promised in the description of the course. So the halting problem is a real limitation of all computers in the real world. No computer is able to algorithmically solve the halting problem. And this is not a matter of like, oh, well, better get to work on that because we just haven't figured it out yet. It's not like that. It's not we haven't figured it out yet. It is logically impossible for this to be a solvable problem by a real world computer. Something that's a little disappointing about this is the halting problem is extremely abstract, and it will take you several minutes to explain to somebody else what it even means. I will just say there are other, I'll say, more ordinary seeming I'll call these more ordinary seeming uncomputable problems. And this will be what I want to talk about next time. Maybe I'll leave it at here for now. But we're going to talk about at least two more problems which seem very down to earth, but it turns out are actually impossible to solve using Turing machines or any real-life computers. All right. So that will be for next time. Sorry for all the extreme abstraction today. It's the last week. Please let me know if you have homework questions. I would be happy to chat about it.